Welcome back to another AP Physics 1 topic video. This one I'm going to tackle one-dimensional equilibrium for dynamics. So let's get right into it. So our first part here is just our facts of physics. So I'm going to briefly explain some of these, but feel free to take a screenshot of these, or in the description down below I have the link to the full fact sheet for dynamics. So what we're going to talk about today is going to be equilibrium. I'm not going to worry about stuff at an angle for the moment. And this is basically the introduction to the force unit. So the most important thing in this that I'm going to go over here is that a force is a push or a pull that acts on an object. And really, what we have here, the most important thing I think in this when we make free body diagrams, is for all forces other than the force of Earth, which is going to be our force of gravity, objects must be in contact with each other to experience a force. So that's important for things that are standing on a scale, or say with our first example, tension. So we'll get more into that when we do our examples. We also have here that the units of force are newtons, named after Isaac Newton. Now when it comes to solving equilibrium problems, there's a two-step process for this. So again, when something is in equilibrium, it is either moving in a straight line at constant speed, meaning there is no acceleration, or it is at rest, which is the simplest version of equilibrium. The two-step process for this is to draw a free body diagram, which I will go into great detail when we do both our examples here. And then set up two equations. So you're going to have that your up forces equally down forces. If those are present, and they should always be because gravity is always working downwards, at least on Earth. And then left forces equal right forces if they are present. And then we have at the bottom here what a free body diagram includes, and again I'll do this in each example. So you have a labeled arrow representing each force. Each arrow must begin on the object, and the object's going to be represented by a dot. And it's going to point away from that object. So it's not going to be, even if I have, say, a push, I'm not going to put the arrow going into the object. It will be going away from it. That's very important. And with this is not a requirement for the AP exam, but I feel like it's important to understand what forces are working on each other, and then it makes Newton's third law questions very, very easy. A list of forces indicating the object applying the force and the object experiencing the force. Again, I'm going to explain why this really works for Newton's third law force pair questions, but we'll get into that later. So let's get to our final facts here. Our final facts here for mass and weight and normal force. So mass just tells how much material is contained in an object. Essentially, if you went to a different planet, your mass would not change because it's just how much of you exist essentially. Versus your weight is dependent on the gravitational field strength of a planet. So this is the force of a planet acting on an object. The equation for this is going to be Fg, which is the force of the planet on the object, or better known as the force of gravity, equal to the mass of an object times the gravitational field strength of the planet. And I have everything, what that means next to it, and that's on the AP Physics 1 equation sheet. And then we have here on Earth's surface, the gravitational field G is 10 newtons per kilogram. That means on Earth that 1 kilogram of mass weighs 10 newtons. Normal force is a force of a surface on an object in contact with the surface. It will always be perpendicular to the surface. This does not mean that the normal force is always straight up and down. It just means that wherever you have a surface, it is perpendicular to it. For these situations that we're going to deal with today, we're not dealing with inclines. That becomes really important when you have an inclined plane. Platform scale reads normal force. This also includes a force plate. So let's get into our first example. So example number 1 of 2. The examples will be linked in the description down below for this video, as they will with all the videos that I'm going to do from now on, and you will have in the link description, linked in the description down below, the fact sheet as well. So if you did not take a screenshot of the facts beforehand and you just wanted a concrete paper of it, they're linked there. You can print it out, do whatever you want with that. So the situation here for example 1 is a 2.5 kilogram block hanging from a string as shown below. So if you had the situation in the class, it would be a mass on a string. The teacher would either use a spring scale to get the measurement and verify, or they're going to use just a force sensor. I like to use the force sensor to show everybody at once on the board, but a spring scale is sufficient enough as well if you don't have the capital for a force sensor from one of the companies that make them. So for this situation, we're going to start off with our free body diagram of the block. So again, going to my fact sheet, I'm going to look at what I need to do for a free body diagram. It says a label arrow representing each force. Begin on the object, which my dot is going to always represent the object. It's an easy way to create the free body diagram, and that's how the AP test has it as well. And it's going to point away from my object. Then after this, even though this is not required, it is recommended, it is much easier to do to explain what's actually happening, that we have a list of forces indicating the object applying the force and then the object experiencing the force. So my first force here, as I should always have, or pretty much always have on Earth, is going to be the force of gravity. And last time I checked, gravity is working down. So I'll have my arrow here pointing away from the dot, and I'm going to label that F subscript G, because I said earlier that FG is equal to MG. You could also have it as just MG. That is acceptable based on the AP grading rubric from a few years ago. So with this, now I'm going to label what this is, or annotate what this is. So we have FG, and I know a lot of you are going to say the force of gravity on my block, but gravity is not an object. The actual object that is creating gravity that we are on right now is Earth. So we're going to say the force of Earth on the block. Oops. So the force of Earth on the block. So now anything else that we have here must be touching the block. And I can see based on my purple diagram over here, the only thing that is touching the block otherwise is going to be my string pulling upwards. So you can call this anything you want. We get a lot of force or Fs for force of a string. Typically you see it as the force of tension, because Fs is going to be the force on a spring, typically based on the reference table. So I'm going to deal with just F subscript T here. But again, you can name this whatever you like as long as you explain it. You can make it F subscript Z if you'd feel like, as long as you say this is the force of the string on the block. So again, it doesn't matter how long you make the arrows here as well, unless the AP exam says specifically to do that, which sometimes they do. So we're going to do here that Ft is going to be the force of the string on the block. And it really is just that simple for my free body diagram. Just make sure you know when to stop with it. Right now, there's nothing else touching the block, so there's no other forces present. Again, anything in order to have a force needs to be touching the block in AP Physics 1. We're not dealing with electrical forces or anything like that besides the force of the planet on the object. So that's going to be part A here, drawing the free body diagram. Again, this lines up with the worksheet I have in the description down below. So let's move into part B. So part B, we're going to write the equilibrium conditions for this block. So this is going to be straight from your fact sheet, and just starting off with our fact of physics, which is our evidence. We then go to our reasons, just kind of explain the fact, and then finally my claim, which is my answer here. So looking at my fact sheet, I just want to see what exactly is here. For my equilibrium fact, if I look at the very top of the fact sheet, it says an object is in equilibrium if it is moving in a straight line at constant speed. This includes an object remaining at rest. So this is going to be my evidence. That's my first part here. So an object is in equilibrium. That's my fact, straight up from the fact sheet. If it is moving in a straight line at constant speed, this includes an object remaining at rest. So if I'm going based on superhead claim evidence reasoning, I do evidence, reasoning, claims. That's my evidence. So now I look for something to explain this. So usually I start off with like, since the block is doing this, that's basically my reasoning. So in this situation, what part of it can I use? It's not moving. It doesn't say anything about the object moving. Essentially, this is a block just at rest in the front of the room. So I can say, since the block is at rest, that could be my reasoning. So that's my little explanation of this fact of physics. So my reasoning is, since the block is at rest. That's explaining my fact a little bit. And then I want to make the claim based on this. So we're saying now that an object is in equilibrium if it's at rest. I'm saying the block is at rest. So now I can explain that since the block is at rest, so the block is going to be in equilibrium, which is going to be my final claim here. So I can put this as my last bullet point, and the block is in a state of equilibrium is going to be my claim. So again, you've heard of claim, evidence, reasoning. This is just a play on that. Evidence, reasoning, claim. I start off with my fact of physics from the fact sheet. I explain that fact a tiny little bit, and I give my answer here, which is the block is in a state of equilibrium. This keeps you from just saying at the beginning that the block is in a state of equilibrium, even if it's not, which in this situation it obviously is, and then going off on a tangent trying to prove that. Instead, I start off with what I see, which is something at rest, and then I say it's in equilibrium based on my fact of physics. It's a good way to essentially write out your notes while actually doing something with them instead of just writing them out for no reason. So let's get into part C. All right, so part C is going to be our actual calculation here. So calculate the tension and the strain. So we figured out our free body diagram. So go back to that point in the video. You should have it written down at some point because we're going to use that in order to make this. And we're going to look at our solvent equilibrium problems 2 steps towards this. And our first step here is to draw a free body diagram, which we did earlier. Break up any forces at an angle, which we're not dealing with right now. And then set up 2 equations. So just to remind you of what the free body diagram looked like without the explanation of everything. We had going downwards the force of Earth, which is Fg, the force of Earth on my block, and going upwards Ft, which is the force of tension, or the force of the strain on my block. So when we make our equations here, I only have up forces and down forces, no right and left forces, so I can say here that up forces equal down forces. And I'm going to use my free body diagram for this. So my up force here is the force of tension, or the force of the strain on the block. And my down force is the force of gravity, which is the force of the Earth on the block. And then I want to look at my equation for Fg. So we said that Fg is equal to mg. So let's go 1 step further. So that's why you can start off with mg if you'd like. You can eliminate that first step. So Ft equals mg, and now we can plug in to get our force of tension. And then if you have the proper equipment, you can actually go ahead and test this. But 2.5 kilograms is usually pretty big. You can do this with like 1 kilogram and test it. We have our factor that's 10 newtons, so you could go ahead and test that if you'd like, if you have a spring scale or something like that, or there might be a simulation online you can find. So our mass here is going to be 2.5 kilograms. And then G is always going to be 10 newtons per kilogram. So your teacher might do it as 10 meters per second squared. It's the same exact thing. The units end up being the same. This is just a way to kind of show how we end up with newtons, and that kilograms cancels out essentially. But same exact number. Your teacher also might use 9.8. That's also fine. 10 newtons per kilogram is just easier to work with, and the AP exam is totally fine with you using it, so I don't see any harm in making the calculation easier where you can. So now all you're going to do is plug this into your calculator real quick. Kilograms will cancel out because you have kilograms on top and kilograms on the bottom. So just making sure you get your answer here, 2.5 times 10. And you should end up with a force of tension of 25 newtons. So if you did happen to have a 2.5 kilogram block and the proper equipment, you can go ahead and test this, or you can try this with other equipment in your physics classroom if you had to stay over for extra help or something like that with the same similar calculations, and you should get a proper answer to see that physics does indeed work. So here's example number 1. So let's move into example number 2. All right, so example number 2. Again, these examples are in the description down below. We have a force plate reads a value of 800 newtons when your teacher steps on. Draw a free body diagram of your teacher. All right, so we talked about earlier and on our facts here that we have a platform scale reads normal force. This includes a force plate. This is a normal force situation. But let's start off first with the force that we pretty much know is going to be in every situation on Earth. And if we have our teacher here, we know that the force of gravity is going to be pulling down, or the force of the Earth on our teacher is going to be pulling down on them. So we have here Fg. So again, follow your steps for a free body diagram in the fact sheet. So Fg, last time I checked, gravity is pulling us down, so we have that going downwards. And again, I'm going to annotate this on the side. So Fg, that is the force of Earth on the teacher. Then we also must have another force because they are in contact with a scale. So think about standing at a scale. A force plate is a very fancy scale that is quite expensive because college track and field teams use them and college football teams use them. But it's just a fancy scale that reads in newtons and goes straight to your computer if you had the proper equipment. So essentially, if you're standing on the floor, you must be in contact with the floor, or you're standing on a scale, you must be in contact with the scale. So it's going to be pushing upwards. So I have a force pushing upwards. And when we're in contact with a surface like this, we call this the normal force. Again, because it's perpendicular to the surface that I'm on. So this is always going to be F subscript n, or a lowercase n is also fine. And my normal force, Fn, again, when we annotate it, it's the object on the object. So for this one, is going to be the force of the force plate on the teacher. All right, so it is that simple again. There is no other forces present in this situation because I'm not moving side to side. I'm just standing on a force plate. I can draw out the situation here if you'd like. So there's my force plate, and then there's me on the force plate, or should be in contact with the force plate. There we go. Oh, that's way too big. So there we go. So I'm on the force plate. I'm not moving. So we have there the force of gravity, or the force of Earth on me, pulling me down. And then the normal force, which is the contact force, pushing me upwards to keep me in equilibrium. So it is that simple for that one. We just have those two forces. So let's move into part B. So now we have part B, which is very similar to part B from example 1, where I write down the equilibrium conditions for the teacher. So again, this is our ERC situation. So we're going to start off with my evidence, which is a fact of physics. Then we're going to do our reasoning, which is kind of just explaining that fact of physics for just like a brief line there. And then your claim is your answer. So instead of just having the answer that says they're in equilibrium, you have an explanation of this, which is a very important idea for part 2s and just for conceptual understanding of AP Physics 1. Again, the whole point of this is not just the math. So with this, I'm going to again look at my fact sheet. And I'm going to look for a fact for equilibrium. And I see at the very top that we have an object is in equilibrium if it is moving in a straight line at constant speed. This includes an object remaining at rest. So we have here that object remaining at rest. If I have a teacher on the scale here, they're at rest. They're not moving back and forth. They're just standing there. So that's going to be my evidence. So again, there it is. We have an object is in equilibrium if it is moving in a straight line at constant speed. This includes an object remaining at rest. So this is our evidence here in our ERC. Then we're going to have our reasoning. So very similar. We're just going to say, like, since this is happening right before our claim, so since our teacher is at rest, that's going to be our reason, or our reasoning here. So since the teacher is at rest, that is going to be our reasoning or explanation of our fact here. And then we want to have our claim finally. So our claim is just essentially the answer here. Are we in equilibrium or not? We've said the teacher is at rest. The fact of equilibrium includes something at rest. So we're going to say the teacher is at rest here. So that's going to be our claim here at the end of the day. So the teacher is in a state of equilibrium. So that is our claim. So let's move into our final part, which will be our calculation here. All right, so part C here is our actual calculation here. We have calculate the mass of the teacher here. So let's remind us of our equilibrium solving process. We start off with our free body diagram, which we did in part A, which I'll redraw here again. So you have the dot here, which represents the teacher. You have Fg going downwards, which is the force of Earth on the teacher, represented by just Fg. And then we have going upwards the force of the force plate on the teacher, which is represented by normal force Fn. So now we can look at our equation here, set up our two equations. Our first equation would be up forces equal down forces. I don't have any left or right forces based on this free body diagram, so we're only going to go with one of the two. So up forces equal down forces. So for up forces, our up force here is represented by normal force, so we're just going to put in Fn. That is equal to our down force, which is the force of Earth on the teacher, which is represented by Fg. Then we can go one step further. Here, normal force is equal to, we say that Fg is equal to mg. That is a fact of physics, so the mass times the gravitational field strength of that planet. Then, one last thing, we are going to be solving for mass. So let me just do a tiny little bit of algebra right here. So I have mass times gravity is equal to Fn. So whenever I want to get something by itself, which is going to be mass in this situation, is being multiplied. So let's do the opposite. So we can divide by g. Divide this out. Divide by g here, and I have that the normal force Fn over g should equal my mass. So now we can plug this in to our equation that we've created here and get the mass of the teacher. So we have here, and it's going to be in kilograms, of course. So we have here Fn is going to be the value of the scale. So again, say like cool little tidbit, when you are on a scale, is actually reading the force pushing up on you, not your actual mass or weight. So if you push down on it, it will actually go up. But go test that if you have a bathroom scale at home. Normal force here is 800 newtons, because again, that is the force of the scale on me, and that's what it's reading. It's pushing upwards on me to get that value. And then G is going to be 10 newtons per kilogram, because we're on Earth. Didn't say anything about being on a different planet. And then we have this is equal to our mass. So with this, newtons is on top, so newtons will actually cancel out, and kilograms will come to the top. So just put 800 divided by 10 in your calculator, and you should end up with 80 kilograms for your mass. So M is going to be 80 kilograms, and that will be my final answer. So if your teacher comes up with 800 newtons, if you do have a force plate, and you ask them what they actually weigh, That's what it is in kilograms. You can then figure it out in pounds if you're in the US. All right, so I hope these examples were helpful. Again, they're all in the description down below if you want to follow along yourself or just come up with different numbers and try it for yourself as well. And have a great day.